So good evening, everyone. We'll start the class by 10 past 6. Sorry, I'm facing some network issues, so it will take a couple of minutes to connect my iPad. So let's start the session. So, welcome to this problem solving session week number 8, which is like we have come to the nearby two-third of this course, and the course title is Sensors and Actuators. And my name is Shomnath Bhattacharjee, as you all already have been known. So, I am currently pursuing my PhD in IIT Jodhpur in the Department of Electrical Engineering, and I have been working on the domain of flexible and organic transistors for neuromorphic computing applications, and our class schedule is on every Sundays from 6 to 8. So let's check this. So this is our course content list, where we have already completed this much of the course, where we have learned about the basics of sensors, and we have learned about the fabrication of these sensors, the environment it requires, and everything. So we have come this far to even like thermal evaporation and sputtering. We have known about sputtering and all these things. And further we have known about vapor phase depositions and chemical depositions like ALD and these things. And now we need to know more about this photolithography, where which we have already learned. So as I have discussed it in a like a very broad spectrum, so I won't be discussing it like again. But oh sorry, I just forgot to start my camera. Yeah. So as like we have already discussed about this photolithography, we won't be going into this detail of this photolithography, and we have also already known about PR. We have already known about the different kind of masks and the steps required for photolithography and everything. So we won't be going very deep into this. So we'll have a recap. If any of you have any kind of issues, we'll discuss that as well. But for now we'll only directly focus on different kind of things. So here, in the last class, we have learned about phase vapor deposition, where we have learned about again sputtering and thermal evaporation and those things, and about various equipments and what kind of equipments are there, and so on. And now in this class, we'll learn about photolithography in more in depth, where I have already discussed that. I won't be going into that much detail of this. And then further we have known about the shape memory alloys. We'll discuss that in a greater depth. So this module is known as the photolithography and shape memory alloys, where we learn about the primary. So previously we have known about different kinds of baking, so hard baking, soft baking, and why they were required and everything. And further we have learned about spin coating of the PR, developing of the PR, etching of the metal, and these things. So we have learned about these things for photolithography, but we haven't been able to discuss this primering thing. So why do we need primer? What kind of a primer is normally used and these things? And then we'll learn more like nitty-gritty things about photoresist, and why these kind of photoresist is very different from different organic polymers and these things. And further we'll learn about the shape memory alloys. Okay. So let's move on to this primer. So in general, the one of the most used primer is hexamethyl disilazane, or HMDS. Okay. So what does this HMDS do? This HMDS is spin coated on top of the substrate, like mostly in case of like silicon wafers and these kind of a things, and it is heated at 200 to 250 degrees centigrade for about a minute. And because of this then afterwards we normally what we have learned about, like we'll deposit the PR through spin coating and these kind of a things. So can anyone tell me, why do we need primers? What is the need of these primers? Why do we need these kind of a primers in it?
To improve photoresist bonding.
Not bonding but adhesion, right? So if we have, let's have these kind of a, like we have a silicon wafer like this, and this is stuck on top of this spin coater. So if we gonna just drop the photoresist here, and with respect to the spin coating and everything, it will spread out, right? But before that, if we use a primer, sorry, before that, if we coat it with a very thin layer of a primer, what it will do is that it will increase the hydrophobicity of the surface, and then it will help the photoresist to be equally distributed throughout the substrate or sample, whatever you say. Okay. So the main thing of this is promoting addition between the substrate and photoresist. So like if we don't use this this HMDS or a different kind of a primers, what will be the problem? The problem will be like that this PR, or like let me write it down here as well. So this PR or the photoresist will detach from the substrate completely, or you can say it may lift or it may peel off. Everything is kind of the same. So it may peel off from the surface, it may lift. So like what's the difference between peel off? Peel off is kind of a, like if there is a layer on top of this, it will peel off completely. But in case of lift, there may be some areas where it is like not even. So with spin coating, we expect a very even film throughout the surface. But without these kind of without the primer, let me write it down that as well. So without the primer, the PR may detach from the surface, and because of that there will be some problems. So like the major one is obviously the pattern failure. So our desired pattern won't be like easily what do I say, like easily be copied, let me say as a copy. So it won't be easily copied onto the surface, the intended surface. Another thing is that it also if we use a primer, so without this primer there may be some presence of some ragged edges. So there might be some ragged edges due to this. So let's say your intended pattern was like this, and but in reality what will be like, this will be like this. Not everywhere. There might be some place which is very smooth and everything, but in somewhere there will be some ragged edges. So you will have your pattern, but if your pattern is very small, then the problem will occur. So it's completely about photolithography. So let me remove this PR point here. Okay. So what I was saying that with the use of primer, the main thing is that will improve the addition, and because of that addition what will happen is that will also improve the pattern fidelity. So anybody knows about fidelity? What is fidelity? Can anybody explain what is fidelity? So like fidelity I can use in a sentence like high fi, like high fidelity or high fidelity, whatever you say. And then it can be used for wi-fi and these things as well. A very easy explanation can be found from Wi-Fi as well. So Wi-Fi is wireless fidelity or fidelity, and hi-fi is high fidelity or like these things. So can anybody tell me what is fidelity? What this fidelity means? Anyone? It means fidelity oftentimes means high quality, but how does this high quality comes? This high quality comes from the degree of accuracy. So how accurate is your pattern? So that means pattern fidelity. So it will increase the pattern fidelity or fidelity based on that how much accurate can your pattern be. So if you are removing this ragged edges and everything, so it will improve your pattern fidelity. Okay. or like in normal sentence or something like he has a very high fidelity with his company, that means he is very loyal or he is very faithful to his company, and these kind of things can be like explained for pattern fidelity. Apart from that, another thing is that it will also sorry enhance resolution. So both of them are kind of connected, but enhancing resolution means now you can use it to have a very good pattern, a very small size pattern with a very good resolution and these kind of things. So your the smallest smallest unit will be much smaller than in case of if you are not using a primer, right? Now, so after this primer, after heating this primer on top of your surface and everything, you will normally coat your PR and everything. So we know that PR is of two type, right? PR is of positive and negative. So based on your need, you can use this kind of a PR. You have two different kind of masks as well. So based on your use case, you have this bright field mask or BF mask, and you have the dark field mask or the DF mask. So based on your use case and everything, you have to choose this between these, and based on your this choosing, you will have to optimize your process as well, right? So why process optimization is necessary? Because you need a very high fidelity pattern with a very high resolution and everything. So you need to optimize your process. So based on if you are using a positive PR or a negative PR or a specific PR, you need to optimize your spin time, velocity, everything. Apart from that, you need to optimize your pre-bake heat and time. Similarly, post-bake heat and time. Everything needs to be optimized with respect to each of your chosen. So for your like let's say you have to get a specific pattern, and to get that exact pattern you will need to optimize your PR. You need to choose a PR at first. So based on your use case, do you need a positive or negative PR? Based on your use case, do you need a PF or DF mask? And after choosing that, you have to optimize that process, like how much spin do you give to the PR, how much PR do you need to also sorry uh, amount of amount of PR is also necessary. So how much PR are you dropping on top of your each of your substrates, and what is the velocity of it, what is the spin time of it and everything. So you need to optimize everything. Just a second, give me a second. Sorry. Okay. So based on your choices and everything, you have to optimize your process and to get the best out of your process and everything. Okay. So beforehand, I have also discussed about this. So we are always talking about this like a single step photolithography. But in most of the fabricated sensors and everything, you will have to use this single step one multiple times. So sorry, multi step. So you have to utilize it for multiple times. So whatever this, so can someone tell me that if we are using a multi-step photolithography and if we are using a single step photolithography, so what's the difference between them? So we know that obviously we have to repeat everything, let's say you have a three-step photolithography, so you need to make three different kind of patterns onto a single device. So you will need to have all the resources three times, and you will have to do everything three times and everything. That's fine, but my question is that what's the difference between these? So what are the technological challenges as well? So like with the next step of, let's say we have a two step photolithography. So what's the problem with the next step? So whatever I'm not framing the question clearly. So my question is that what will be the problem in the next step that we have to remember about the first step? Can anyone try to answer it? So like with the multi-step photolithography, what's the difference between that with a single step photolithography? Just guess it.
Device complexity.
Yeah, device complexity will be like much higher, obviously. And any other things? Obviously, device complexity will be much higher. So if let's say if you are going for a structure like this, some cantilever structure kind of a this, so like this, let's say. And if you are going for a structure like this, and so this is like this, and on top of that, you also have another different kind of a pattern here. So this is a completely different step. This is a complete different step, and this is a complete different step. For whatever reason you are making this. So obviously the device complexity will be an issue. Apart from that, anything? Let's say you are making this is a complete single step. Let's say this is a complete single step. Let me remove this. So this is a single step, and on top of that, you are making another step like this. Any other problems you might face? You can use the chat box as well, so like I can see it from there as well. Let me answer that. So, apart from the device complexity, there's another major issue. What is that? That is, you need to understand the the structure. No, not necessarily. So, what depending on your design, so it may be weak or it may be strong or something like that. So, if, let's say you want to make a pillar like this on top of your structure, right? So you can make it like this, or apart from that, what you can do is that you can make a sacrificial layer like this, and in the next step, you can remove this. So it will be weak anyways. So if you want to, let's say you can have these kind of, because it's a cantilever, you can't have any kind of a support there. But if you are making a support with the second step, it is also viable, right? So not the structure weakness, but you have to understand the interaction of the new steps or the materials with the previous pattern. So what I mean to say is that, so if you have a pattern like this, let's say the blue one is the first step. So you always need to understand if your new material, if your new PR, or if your new metal will hamper or interact with the first pattern with some kind of a way. So you always need to understand that if the red one is the next one, you always need to understand if this metal is enough. Just a second. If this blue structure is enough to withstand the whole this complete red metal or something like that. So you need to understand that how will the new materials, how will the new steps, and let's say you are etching the new metal, and while etching the new metal, your old metal is getting etched away. So it's a problem, right? So you need to understand that while you are using it for multi-step photolithography and everything, so you need to understand that you are not disturbing or destroying the previous step, like previously made patterns or something. So even it's, let's say you have made that about a day or 2 days ago or something like that, it doesn't matter, that it won't hold off against etching or some kind of a thing, right? So you need to understand that your previous pattern doesn't get destroyed because of the new patterning or new process or something like that. So this is the basics of photolithography. And if you have any like queries about anything about related to photolithography, I'm like you can ask me right now, because like I'm not going into too detailed of this photolithography and everything, because in week 3 4, around week 3 or 4, I have already discussed about different kind of a masks, PR, and the process and everything. So I'm not going into that much detail of this photolithography. So anybody have any questions regarding what I have like discussed right now, or previous things?
Sir, I have a query, sir.
Yeah, yeah, sure.
Uh, in double beam cantilever structure, sir,
Hmm.
how we can perform photolithography uh, in single push structure mean we add the mask layer and peel it off, but in double stand beam model in photolithography mean how can we model it, sir?
So, can you show me a drawing or something like that? That whatever design you are talking about.
Sure, sir.
Yeah, just share your screen or something like that, and then we can discuss it.
Hello, sir.
Yeah.
Sir, sorry for interruption, sir. The camera is not properly working. For cantilever, for RF MEMS structure designing, example, right that, sir.
Um, just a second. So, like, can you share your screen or something like that? So, if you are not using your camera even,
No, sir, I watching phone, sir, mobile phone.
yeah. So, like, can you share the screen, because it's available for everyone, right? This the third option, not your through your camera. Just take a picture of your like whatever you have drawn, and then share your screen, phone screen. So there can be like two different, yeah. So maybe, yeah, it's visible. No, no, it's fine, it's fine. So this way I can also understand. Just tell me what is this. Your voice is muted, my like I'm not sure what. Let me check. Your voice is muted. Yeah,
Sir,
yes, yeah, yeah. I can hear you.
uh, in the structure, left and right are Si silicon dioxide. Okay, sir.
Can you show the structure again? So at that time I was not able to.
Okay.
Yeah. So you were saying that there's a air gap in between,
Yes, sir. The
and
left and right are silicon dioxide support for the
okay,
top
okay,
metal layer, sir.
yeah,
In between metal and lower silicon layer, we have an air gaps like a structure, sir.
okay.
So by creating the structure, mean how we can make the photoresist on this, sir? Because to create air gap in between metal and base silicon layer.
Oh, you can easily do it, right? So you have to use and like okay, let me share my screen and then I can tell you. Just a second. So like your structure is something like this, right? Sorry, just a second. Let me use this. So you have a substrate like this here. You have some pattern or something like that was there. You have this two beams of silicon dioxide,
Yes, sir.
and on top of that there was a this structure of metal, right?
Yes, sir.
Yeah, so this was your structure. So to make this, the best way to use is you have to have a sacrificial layer. So what you have to do in the first step, uh, maybe I'll draw it here. So let me take it away from here. So just a second. Okay. So this was your structure here, and now you need to make this structure, right? So this was your silicon dioxide, this was your metal. So in the
Yes, sir.
first step, what you have to make is this is your basic substrate. On top of that, you have to pattern this silicon dioxide, this here, like you have to deposit silicon dioxide, and in between, if there was some kind of a pattern, you have to make it separate ways. Okay, so this is after the first lithography step. In the next one, what you have to do is that first you have to prepare a sacrificial layer. So in between these, you need to have a sacrificial layer, and so this is completely your sacrificial layer. Okay, just a second. This is completely your sacrificial layer, which you will remove afterwards, not right now. And on top of that, now you will pattern your new metal. So whatever that metal is, and you have to like pattern that metal, or you have to deposit that metal based on your. And after everything is done, you just need to dissolve this sacrificial layer. Okay, so you need to just dissolve this sacrificial layer, and so there you need some kind of a like sorry, just a second. So you need some different kinds of PR. If you need to use PR, so you can have two different kinds of PR based on to this different kinds of steps. Otherwise, what you can do is that you can use a just a second. Otherwise, what you can do is that you can use a very simple simple metal that can be etched away very fast that than this kind of metal. I don't know what kind of metal you are using or something, but you need to have a metal that can be easily etched away like copper or something like that. And on top of that, you can just make this structure is silicon dioxide, and on top of that, So I am not sure what is in between here. So if this is a very fine like fine detail structure or something like that, then you have to use three different steps of photolithography as well. So in the first step you have to make this. In the second step you have to make these beams of silicon dioxide, and then on top of that the final beam, this final metal will be there. That is your third step. And finally you have to dissolve this in between thing. So I'm not sure what's that in between structure, that the small structure was there, but if that's a very fine structure, you have to use three different steps of photolithography as well. Is it
Thank you,
clear?
sir.
Yeah.
Yes, sir. Thank you, sir.
Yeah, sure, sure. So now if anybody have any questions, you can ask me. Otherwise we'll move to shape memory alloys. Or you can ask me after the class as well. So like after our question answers and everything. So now let's move on to the shape memory alloys. So what is a shape memory alloy? This is a phase transitioning metal or phase transitioning alloys. What they do, they is like so at a very low temperature they have a very original shape, and if they are bent through some means, and they hold a very at that same temperature. So if it's a very low temperature and at the same temperature this is deformed, so this is bent, right? So if your alloy was like this, you have just bent that to a different shape, or like let's say like this as well. So you will have a different kind of a shape. When it's heated, it will go back to its original shape, that before the bending and everything, it go back to the straight shape. So this is called a shape memory alloy because it memorizes the original shape. So the main thing is that it memorizes the original shape. It was it. So it go back to, if it was a circle, it will go back to circle. If it was a straightened bar or something like that, and it will go back to that. So these kind of a memory, alloys show a kind of a memory kind of a thing. So like what do we mean by memory? Memory is like if you can remember something, so it remembers the shape it was in previously, right? So this is called a shape memory alloy or SMA. So apart from this SMAs, there are also like smart memory alloys as well. So I'll talk I'll discuss that in a bit. But so these shape memory alloys can be used in different kind of a ways. So I have taken this from a journal directly, and it was their figure. So where they have shown that utilizing different fabrication properties like the casting. So the casting is one of the best ways to use a shape memory alloy, apart from that additive manufacturing and powder metallurgy. So like in different kind of fields, so you can see that casting can be done by electronics and electrical engineers, and additive manufacturing is mostly towards mechanical part, and powder metallurgy is completely towards metallurgical or material sciences. So in every other domain, people are using this shape memory alloys, and the materials are these. It can be copper based, ferrum that means sorry iron based, copper based, or nickel and nichrome and these kind of a things. So they have this. So it can be made out of springs. So why do you think a spring made of shape memory alloy is a very good thing? Any ideas why this springs made of shape memory alloy will be a very helpful thing, and which kind of a application it will be very useful for? Any ideas? So a bar is completely normal, right? So in any kind of a sensor or something, like we'll use this bar and like shape memory alloys and everything. So we'll discuss in the, I guess, in the next module itself. So it's everything is fine. And in this module we also had some demonstrations as well. But why do you think if we make a spring out of this shape memory alloy, it will be cardiology veins, right? Nice. It's a more advanced answer, but like it is nice. Any like normal in a very mechanical way, can you just give an example of this springs for pressure sensing and displacement? So what it can do is that you can make a sensor that will be like that will deform, right? So with a very hard pressure or a hard force and everything, it will deform. Now this deformation can be cured through just heating. So you'll heat the alloy and it will go back to its previous shape, that is a basic spring. So it is very useful in very like large scale of things. But obviously cardiology, veins and these things are the main things they have been used for, right? So as we have already discussed, so like in biomedical engineering and these things we have been using this. Apart from that, different robotic technologies like the arms and like recently I guess you have seen the robo dog and everything. So in those things they have been using these kind of things. In aerospace it's very useful. So wherever we need to have a sensor that is fault proof, so we can't right now it's not possible to make a fault proof sensor or something like that. But what we can do is that we can regain its first position back, so that it is like kind of becomes fault proof, or it like I'll say that we can make it back to the first state it was in. So that's why it is being using in automotive and aerospace, where like we need sensors that are fault proof and everything. So like they have a very like high properties and those things. And so like our main target is towards MEMS and NEMS, right? So this is our main target. Apart from that, in case of solid state cooling and 4D printing and these kind of things, we have been using this, right? Just a second, give me a moment. Sorry for the interruption. Just a second. Let me turn on my camera. So this was the basic thing that chip memory alloys has been used for over this years for the last decade and so. And like we have been using them for MEMS and NEMS and in 4D printing. So 4D printing things, like anybody have any idea about 4D printing? So we know like 3D printing is like is for the masses, right? So we have 3D printers, we have been using it for different kind of a structures, or even for fabrication of sensors as well, like for the past decade as well. So we have been using 3D printing, where the previous sensors were like this, it was in 2D. And right now like for making a 3D structure or something like that, for 3D fets and those kind of a things, we are using like different kind of a techniques like C fets, T fets, and there are different kind of a different fets as well for transitive purposes. Apart from that, for this 3D structure making, we have to always use we have been using photolithography. And for a very high detailed 3D structure, even there can be photolithography steps of 17, 18, or 19 times as well, right? So like what you can do is, like if it's printing supported, or you can optimize that through printing, you can make a complete sensor through printing as well. So what will be the difference in 4D printing and 3D printing? Anybody have any ideas? But you can have a guess as well. Like it's a very new technology and those things. So it's completely in R&D and D and everything. So like Just try to guess it, like it's fine. So 4D means 2D means it have two dimensions, right? And 3D means it has another dimension, that is third dimension. In 4D, it has another dimension. So in case of like movie halls or something, you might have seen like 3D movies, right? So you will have to wear a simple goggles, and based on that, what it creates is like it creates a visual perspective where you are seeing that your the main character of the movie is coming outside the screen and everything, right? So it's 3D, so it's giving another dimension in 4D cinemas and everything. So what they give you is like they will move your chairs, they will like it have a vibration, rotation, and those kind of a things. They will also sprinkle water based on if you are going inside, like let's say a watery place, or in Amazon or something like that, and it will spray water on top of you and these things. So it gives that like touch experience as well, and based on that your body moves and everything. So it gives a 4D experience, so another dimension of your experience, right? So in case of 3D printing and 4D printing, what do you think the basic difference is, or what is the new dimension? Any ideas? So it's very easier to to think about a 3D structure because we have seen so many 3D things, and in through our eyes and everything we are seeing 3D things, right? So how do we make a structure 4D? Response to stimuli. Like, can you explain it a bit more? It's a nice answer, so it's kind of a correct, let's say 90% correct, but can you explain it a bit?
Sir, in response to heat, the shape memory alloy will change its length
Yeah.
so that
So
the,
if I make a 3D structure utilizing the shape memory alloy, what will happen?
so only we can have the fixed shape objects, sir.
So like what you said is like in response to stimuli like heat, the shape memory alloy changes, right? So if we can make a 3D structure utilizing the shape memory alloy, like let's say using 3D printing, so it will, what will happen if we give heat to it? It will change back to its original shape, right?
Yes, sir.
So that shape is changed with response to heat. Similarly, we can have like color changing objects as well. So there are also based on this kind of a stimuli, like based on light and based on things, the color changes. So if a 3D object changes its color, it's
And
kind of a newer
functions
dimension.
will change.
Yeah.
Sometimes functions may change.
Yeah, yes, obviously. So based on if it's nearby to water or something, it may swell. It may be based on that water changes and everything. So that is a new dimension of your functionality. So that's why it is called 4D. So this is the basic change between a 4D printing and 3D printing. So shape memory alloys are a very good option to use for a 4D printing structure and these things, right? So we'll end this here, and then we'll move on to this question answering sessions. So let's move on to question one. So if anybody has a question regarding photolithography or shape memory alloys, you can ask me right now. Otherwise, we'll move to these questions. Well, I am writing down the first question. You can ask me right now. So if you need to ask any question. So which of the following, how to use SMA in mem structure? So in the videos, it was already demonstrated, but let me say that. So if you are using let's say shape memory alloys, right? So what it can do is that it will change its shape based on heat, and if you are giving heat, it will change it back to the original shape, right? So in case of let's say in memes, like in names or memes, anything, so what it can do is that so like in the thing, so let me, maybe here I can draw it. Just a second, right? So what I was saying is that, let's say you have a structure like this, right? Let's use the whole thing. So if you have a structure like this, both are identical. I'm like, let's try to make it more identical, right? You have a structure like this, and you have a, so this is a movable structure, right? It can move around. And you have a structure like this. This is a fixed structure. So this is a fixed structure, and this is a movable part of that structure. So now, and this is not a single strand, right? So it is like this, and this is also like that as well. So based on the structures and everything, you can use it for like the based on the design, you can make it as an accelerometer, you can make it as a gyroscope and everything. So to make this movable part completely movable and detached from the fixed structure, what we use is that we can use springs, right? So based on the springs, they will be connected. And so if you are utilizing this kind of a accelerometer, or let's say you are utilizing them, so like the structure is not like, doesn't look like this, but this is a one of the basic kind of a structure where if you move around, the spring will change, and this spring is made of SMA, right? So even if they get destroyed or something like that, based on the heat, the spring will came back to its original shape, and the device will be kind of a undestroyable kind of a thing. So like one of the most utilized way to use this. So that's why it's completely like shape memory alloy is one of the most used material in case of mechanical engineering as well, because they can be used for creating mechanical sensors like the accelerometer, gyroscope, and these kind of things. So apart from that, there are several like, so I am just making this only two, but there will be like multiples, right? Otherwise the movable part won't be like completely connected to the fixed surface as well. So based on this, so let's say if you are making like springs utilizing silicon or some kind of a thing, so what will happen in those cases, that with the like, let's say with a long term usage and everything, they will get like, they will get destroyed. I won't say destroyed, but displaced. And based on this displacement, there will be errors in the measurement. So in those cases, it will be better to use a SMA, that is shape memory alloy, in those cases, right? Mm, we can use photolithography to deposit it. uh, I didn't get your second question. Can you repeat that again? So, like, let me write it down at that time and try to like rephrase your question or something like that. I didn't get that. So, the main thing is that it have a very large strain based recovery, right? So if your basic silicon based spring or something, it will get destroyed or it will get displaced, but this memory alloys will be able to recover, and it will kind of make this an undestructible. Obviously if you use a very huge force and everything, it won't get back to its original position, but in most of the cases with a very small strain or a very mid level strain or something like that, it will go back to its original space. And also what it makes is like it have a very high power to weight ratio as well, that is very helpful in these cases as well, right? Can you rephrase your next question as well? I didn't get
Sir,
that. Yeah.
uh, to make this spring structure in micro scale to
Mhm.
hold the membrane, silicon membrane, sir. This is my question, sir.
So
To make
like,
this
yeah.
in demonstration section also, we use 50 micron SMA rolled in a bolt and heat and they heated, and after that they unwinded and give some electric by using the electrical current, the structural deformation and originals we we understand, sir. But we can design this in micro scale, mean it can hold the silicon or any other membranes like a structure. It's possible, sir.
Yeah, it's possible, but to make it in a very small size or something, it's a very challenging task. It is not entirely for R&D level work or something like that, right? So you need to have a, like, obviously in like in these like any kind of a device like GoPro or something, right? So they need to be very robust, right? They are very robust, right? So you can use it in a very harsh sunlight. So I guess you have seen, right? In if you like, let's say you have a phone, right? So if your phone, you are using it like under a sun or something, it will heat up very fast, but your battery is not directly in contact with the sun or something, right? Your
Yes,
total
sir.
chamber or the total chassis of your phone is getting in contact with the sun, and that battery is getting normally heated through that, and your battery will start depleting very fast. Similarly, if you are using it in a cold weather or something like that, your battery will deplete very fast, right? So what is the
Yes,
problem
sir.
in these cases is that, like, you don't have a cover that protects it from the surface and everything. So in case of GoPro and everything, so you need a spring that is like resistant from these cases. So in those kind of a devices, we anyways use SMA and these kind of a different kind of a alloys as well. But to make it in a very small structure, like, it's also been used in NEMS as well, like nano electromechanical sensors and these kind of things in nanoscale and everything. These have been used, but making it a very smaller structure, it's very like a challenging task as well.
Yes, sir.
Yeah. So let's move on to the questions, I guess. Oh. So the first one is that which of the following can be used to improve the addition. So I have already discussed this addition of PR on deposited nitride layers. The first option is polydimethyl siloxane. Second option is hexamethyl diazoxylisane, and three is hexamethyl disilazane. So which one is best to improve the like addition of PR? I have already discussed this. So like obviously three, yes, that's correct. So what are the other two used for? So the first one is obviously PDMS. We have already discussed about this. This is another form of HMDSO. That's another thing, and this is HMDS. So this is the best one to be used, right? Go on to the next one. Question number two is that which of the following process parameters influence thickness of film deposited by spin coating? One is spin duration, second is spin velocity, and third is both. Just a second, let me open this. So obviously it's both, right? So how does spin duration affect the the thickness of the film, and how does spin velocity affect the duration, like the thickness of the film? How does both of these affect the, so they affect, obviously they influence the thickness, but how does they change the thickness, right? So let me put it in a way. So if I increase the spin duration and if I increase the spin velocity, the thickness will decrease or increase in both the cases, right? Will the thickness increase or decrease?
In duration, the thickness will be increased. So, and if the spin velocity is high, the thickness will be um, very less.
So you're saying if I increase the spin velocity, it will decrease, right? And
Yes, sir.
if we increase the spin duration, the thickness will increase,
Yes,
right? Yeah.
yes, sir.
Others? So in my, I guess in my fifth or sixth lecture, I have discussed about the equation as well. But I'm not asking about how much it will decrease or how much it will increase, but I am asking that if it will decrease or increase, right? So you are saying spin velocity thickness will be decreased. So you are also saying the thickness will decrease, right? So it's correct. So it's correct that the thickness will decrease, but with spin duration, it will also decrease as well. Why? So let's have this. So at a certain velocity, let's say at 1000 rpm, you are getting a thickness of 10 nanometers. Okay. And if, and that is also for, let's say, 10 seconds. Now if you are increasing that 10 seconds to 20 seconds and you are at the same rpm, so you are just diluting the 10 nanometer to a very lower amount, right? So let's say at 8 nanometer, so it will obviously decrease. Similarly, if I increase the velocity, like let's say you have 10 seconds and you have 1000 rpm. RPM means revs per minute, right? So for, because everything, like the spin velocity is also the angular velocity, and now what you are doing is that you are keeping this as constant, but you are increasing the rotations per minutes, right? Or revolutions per minute. So what it does is that it will decrease this, but at a much higher rate. So it will be like, let's say, 6 nanometer or something like that. So it will decrease as well. So in both the cases it will decrease. Let's move on to the next one. Question number 3. Now, which alloy or a smart material was used for or as the SMA? Yes, nitinol. Nitinol was used. So my options were HMDS, nitinol, nichrome, and alnico. So the answer is obviously nitinol. So what is nitinol?
It's an alloy of nickel and titanium.
Nickel and titanium, right? And nichrome is nickel and chromium.
Mm.
Similarly, alnico is aluminium, nickel, right? Sorry, nickel will be this. So nickel and titanium behaves like a smart material or a smart alloy, right? And let me have another question. So why does like an alloy behaves like a shape memory alloy but not in metal? Why? So my question is that why shape memory alloy is an alloy but not an metal?
Depend on crystal lattice, sir.
Yes. So like describe it a bit for others.
The atoms arranging in the crystal structure, they can deform by applying the, they can transfer the two phases, sir, in
Yes.
this.
So it's a two-phase crystallization process, and based on that, metal doesn't have that, right? So because the metal have only a single type of atoms, and throughout that, so it performs a very well-phased thing. But in these case of these special kind of alloys, they have two phases, and based on this, so if you transfer the heat, and based on that, it will remember its previous position. So it's correct, right? So let's move on to the next one. Question number 4. So let me know if it's true or false. Xylene is, yes, to have transitions in crystal structure, right? Is used for the, so is it true or false? And also let me know if it's true or if it's false, then I'll have another question as well. Oh, yes. Right. It is true, right? So it's true. Now let me know why xylene is suitable for this. What? Why xylene is suitable for this? Or let me reframe my question first. So what is deparaffinizing? What does it mean? Let me write it down. Removing wax from FPPE, right? Or formalin fixed paraffin embedded tissues. So removing the wax from FPPE tissues. So why xylene is suitable for that?
It readily dissolves paraffin wax.
Yeah, yes, that's perfectly correct. But my question is that why xylene? Like, can we use another material in case of that? We know xylene is the most used one, right? In the like the demonstration and everything, we have seen that. But why xylene? Can we use another thing in case of that? It like paraffin or wax to seal sample for contamination due to environment. No, my question is why xylene? So like, can we use any other thing in case of xylene? Because the main what I think of, sorry, just a second. So what I can think of xylene is that it is obviously toxic, right? And it also is a irritant as well. Sorry, irritant as well. So if it goes inside your nose or if it goes inside your eyes or something like that, it will irritate at a very high level. It is also flammable as well, right? Flammable as well. So everything has to be done very carefully. So why does we need to use xylene? Can we use any other thing as well? Any other things that like dissolves wax? Is there any other options? So you know, right? Xylene is a VOC, volatile organic compound, right? That is very harmful thing. It is toxic, it is irritant, it is flammable. But why xylene? Like, let me give you some alternatives as well. So, like normal oils, like let's say coconut oil or any kind of a citrus-based things, citrus-based uh liquids. So these are also a good alternative for that. It is not VOC as well. It is not toxic as well because we like use in food as well, right? Coconut oils and citrus based liquids like lemon juice or something like that. So we use it. It also allows further dehydration and staining. So the main thing is that in the newer generation things and everything, people are trying to use this oils and but they are not at par at as xylene, right? So xylene is like is the one of the best options that that is being used, but like oils and citrus based things they are not at par at the like what we are expecting. That they are not at that much level right now, so people have been trying to use like in R&D sectors and everything, people have been trying to use these kind of a things as well, right? So let's move on to the next question. So no, IP and acetone is not that suitable for wax cleaning as well. But like any kind of a biodegradable thing and everything, so like the oils and these things are much suitable than those things, right? Now, what is the purpose? Because like IP and acetone are VOC, but they are much like we can even touch them by our bare hands as well, right? So it will be much easier to use IP or acetone. Purpose of performing um, dehydration big. So there are options to remove sodium, ion contamination generated by touching the wafer with bare hands. Second option is to speed up PR coating. Three is to remove moisture after the wafer cleaning. Four is to replace soft and hard bake. Three, right? Yes. So now I have another question, follow-up question. So obviously three is correct, so I'm not going into the question itself. But what is the difference between this dehydration bake and a soft bake? We know that soft bake is done to like the primarily it is being done to remove the like the remove the excess water and excess solvent and those kind of things. So what is the difference between that with and dehydration bake? Yes, someone raised their hand. To remove water molecules without damage tissue structure. Yes. So what does a soft bake does that a dehydration bake doesn't? Yes, that's the correct answer. I was looking for. Temperature range is quite high in dehydration bake as well. So let's move on to the next one. So this was question number 5, right? Yes, 6. Which of the following are the basic components of a PR or photoresist, right? Which among these are? So your options are solvent, 2 is developer, 3 is sensitizer, 4 is metal nanoparticles, and 5 is base material. So which among these are?
Developer, sir.
So developer is a basic component of PR. So why do we have a specific PR developer? So let me answer it. Obviously the base material. So the PR consists of the base material, right? So we need to have this base material. Without that, the PR is nothing. So in case of any kind of organic polymer or something like that, we have a base material or base powder, right? With that, we have the solvent. So everything is completely soluble inside the solvent, and because of that. But for PR, we need specifically sensitizer as well. So these three are the complete components of a PR. It have the base material, it has the solvent, and it has the sensitizer, right? Apart from that, obviously metal nanoparticle doesn't have to do anything with these. And developer is a complete different thing. So we have a separate PR developer. So what kind of a PR you are using, based on that you will have to choose your PR developer. So PR developer is not part of PR. PR is completely a different thing. So the photoresist is made out of, so red liquid kind of a thing is photoresist, right? So it is made out of the base material, its solvent, and its sensitizer. Now let's move on to the next one. Question number 7. Transition states of a shape memory alloy actuators such as nitinol are, so what are the transition states, right? Martensite and bainite phase. Is it bainite and perlite stage or phase, or it's austenite and martensite phase? Martensite and austenite. So can you tell me a brief about this? Obviously it's the correct answer. It's the correct answer. So can you tell me a brief about this? What are these phases and what does that do?
Initially, shave memory alloy in arsenic state. By train in the training purpose, we make the heat on this. After the training phase is completed, it move to marsenate phase. Then by applying the joule heating, by applying the heat or some voltage to trigger the material by heating, it move to the original state, uh,
Austin, Austenite,
arsenic
right?
state.
Austenite, yeah. So, like, why these names? Any idea of this?
No, sir.
So, actually, this austenite is nothing but known as the gamma iron, right? So this is known as the gamma iron. This is a non-magnetic phase of iron, right? So iron have two phases, right? It has a non-magnetic phase and a magnetic phase. So this non-magnetic phase is known as the austenite stage, where it is known as the gamma iron, and it doesn't have any kind of magnetic properties. It doesn't have any kind of a properties like to hold the magnetic properties. So like it doesn't have any kind of a like properties that it can hold that thing, right? And now we have the and oh, right, another thing to know is that this austenite stage is at a FCC cubic structure. So anybody knows about this FCC structure and these things?
Phase central cubic system.
Yes, FCC is face centered cubic. So it is in a face centered cubic structure where it doesn't have any kind of a magnetic phase, right? In contrast to that, this uh, Martin-Site phase is in a BCT structure. So what is BCT? Any idea what is BCT? BCT is body centered tetragonal. So this is kind of a the metastable state, right? It is not completely stable state. Because of that, it can come back to previous state with like if we are giving it a very much higher heat or something like that. And it is also brittle state as well, right? A very brittle and metastable state, and it can come back to this austenite stage, right? And let me write in phase centered cubic. So what's the basic difference between these is that it is a cubic structure, but it is a tetragonal structure. So it there's a body centered tetragonal structure. So it is obviously unstable because it's a very larger structure as well. But face centered cubic is a very small structure with a much larger number of atoms at each of the faces and everything. So it has a very heavy and smaller structure, but it is non-magnetic phase of iron. And in case of like body center tetragonal, it is a very larger and a metastable and a very brittle stage. So what this transit stage means is that like it is at a very stable austenite stage. Whenever we change this, it comes to the marsenite stage and then a martensite stage, and then afterwards when we cool it or heat it or based on that, it comes back from the metastable state to the stable state, that is austenite stage, right? So with this we'll complete today's session. Thank you for attending today's class, and we'll meet on like next Sunday. Okay. Thank you, everyone.
Thanks, sir.
Yeah. Thank you.